myself. Okay, então, welcome everyone. We're here for the third lecture of Riccardo Muolo on Turing instability on network. And today will be instabilities? Will be directed networks. Directed network. Okay, so have a good lecture to everyone.
Thank you, Professor Stefanella. So, wait, let me. Okay. Yes. Okay. So today I need to arrive at a certain point so that at least I could finish what I prepared, what I thought I would do in 3 lectures. So there is a part that maybe I can skip the details. We'll see how much it takes. Let me set the timer. Okay, so we are studying reaction diffusion systems on networks. We have the reaction part and then the diffusion that is governed by the discrete Laplacian, which is a matrix with certain properties that we saw last time, and which plays the role of the nabla squared of continuous support. And so we have seen last time how we can solve this system by linearizing and change the basis. So study the development of the perturbation, the expansion of the perturbation on the basis of the Laplacian. And on a symmetric network, the basis is orthogonal. And so we could get to the system in the linearized and in the new basis of this form, where we have alpha from 1 to n. So we have one equation, 2 times 2 system for each eigenvalues of the Laplacian, and J alpha is a matrix of this form. U and then G plus V lambda alpha. So you see that it looks a lot like the one we had on continuous support, where we had the minus k squared. And now we have the lambda alpha. Minus k squared, where was the continuous spectrum of the nabla operator. And now we have the spectrum of the discrete diffusion operator. And this is negative semi-definite. So there is one eigenvalue that is 0, and we have the system without space. And then all the others are negative. If the network is connected, there is only one 0 eigenvalue. Before looking at the eigenvalues of this matrix, just one thing, because we will need it later. So in order to get from this to this, we use the property of the eigenvectors of the Laplacian of orthogonality. Okay, now we will deal, hopefully by the end of today, if not beginning of next time, with networks who either are not diagonalizable, and that's a case apart, or that they are diagonalizable, but they don't have this relation. The basis of the Laplacian is not orthogonal, orthonormal. But we can do the same thing that we did last time. So it's the same procedure. Sorry, E1 n, where n is the dimension. Sorry, here is n, not alpha. N is the number of nodes. Where now we need to go to use left and right eigenvectors, and so we still have this relationship. So we do the same procedure, the expansion on the basis of the Laplacian right eigenvector, and then we have to multiply with the left eigenvector to obtain this. And then, so there are this calculation with all the details is probably somewhere, but we put it in a paper that is Carletti and myself of 2022 in chaos, solitons, and fractals. It's a different framework. There's no diffusion, but then there are all the details of this calculation. So now, said that, we can study what happens here. So I'm going to delete the rest. We started from a stable homogeneous equilibrium, so without space. And we know already that when we consider the matrix with lambda equals 0, the trace is negative and the determinant is positive, so that we have stability. So as before, we see that the trace is still negative because lambdas are negative or 0. And we need so to impose the determinant negative. We do the same calculations as before, as the case of continuum support. And we find the same relations. Okay, so I rewrite them here. D, B, F, U. And then the other one that was a bit less elegant, let's say, plus D, B, F, U squared for DU, DV, plus the determinant of J0, where J0 is the matrix without the lambdas, less than 0. Okay, so these are the same as on continuous support, and you see that again we mix the model, so the parameters of the model, and the diffusion. We don't see the spectrum. Okay, so one may think in principle, okay, it's the same case as before. Not exactly, because our spectrum is finite, it's not a continuum. Okay. The dispersion relation, so the real part, the maximum real part of the eigenvalues of this matrix, when considering a continuous parameter, is the same, exactly the same. However, the effective dispersion relation function of minus lambda alpha is discrete. So we always have this because it's the system without space. And the eigenvalues, so the instability mode lie on the continuous curve. So in principle, if we are unstable on continuous support, we should be unstable also on network. However, to take a different network, we could have the following. So we have no instability. Okay. So while these two conditions, together with the two of homogeneous equilibrium, are necessary and sufficient on continuous support, they are only necessary on network. You need also to have that the spectrum of the Laplacian lies in the interval of critical case. Okay, so this is a difference. If you study large networks, you don't care. But if you study small networks or networks who are really a lot connected, so the spectral gap is big, you may have cases like this one where you don't have with the empty dots. And let me see if I told you everything that I wanted to say. Yes.
Sorry about that.
Yeah.
Like the lambda will be the highest value in absolute value
Of this matrix.
Yeah.
Yes. Yeah. And again, as before, there are two. One is always no, so one is always negative, and there may be one that is positive. So these two conditions together with the homogeneous equilibrium, now I'm gonna delete this. They give us the region of instability for the brackellator that again I use because it's very visual. So this is the region of instability on continuous support. But then for this condition, what we have usually is that the instability, the effective instability of network is not the same because the spectrum is finite. So at a certain point, it doesn't go stable anymore. Or if there is a spectral gap, like in this case, with the empty dots, we might have situations like this. And then if we move further, they're gonna separate. And this is a classic example of finite size effects. The parameters of the brackellator model, the reaction rates. I only use it as a visual representation. Okay, so we've seen direct symmetric network. Let's move on to directed networks. Before studying Turing instability, let's see what it means to diffuse on a directed network. So we have, again, a simple case of a lattice, one-dimensional lattice. This is node I. And we have a certain substance on this node. But now we impose that the diffusion can only be in one direction. So the adjacency matrix of the support before, in the case of symmetric network, it was the following. Okay, but now we only have one direction. So depending on the convention that you use, the matrix is asymmetric. So now, what does it mean? This equation. We haven't defined the Laplacian yet. So can we get to something like a diffusion equation, but on a discrete support? Okay, so we had that the Laplacian on a symmetric network had -2 on the diagonal, and then a plus 1 or a minus 1, only the subdiagonal or supradiagonal, they were 1. So now if we say that this is, how did I call it? E plus 1, I minus 1. We can guess that this Laplacian, this new Laplacian, let's call it L tilde, doesn't have 2 incoming directions, but only 1. And then I plus 1 equal 1, and the other direction I minus 1, 0. So this is the guess. Now let's go there formally. Not exactly that formally, but just to give you a like more formal than this, not with a guess. So I will delete everything except this.
For the LII, and
Huh?
LII would be like, it would be -1, but
so in the symmetric case, you had substance coming from 2 directions. So you had -2. But now you only have substance coming from 1 direction. I minus 1, this is the guess. I plus 1, 1. So you have the supradiagonal. And then I minus 1, 0. That's the guess. Spoiler alert, it's correct. So if we go from a microscopic point of view, let's just consider a case in which substance U has a probability A of jumping from node I to node I plus 1, and B from nodes I to I minus 1 in the with A plus B equal 1. So in the case of symmetric networks, we have A equal B equal 1/2. So diffusion is isotropic. In the case that I gave you at the beginning, we have that A equal 1 and B equal 0. So those are the 2 extremes. Let's just do it for general A and B. And then, of course, you have all the other nodes of the lattice. So the variation in UI is given by what is coming from I minus 1 with coefficient A. Did I name it the opposite way? No. Okay. And what is coming from I plus 1 with coefficient B? Okay, minus what's going out. So A plus B UI, and this is equal to 1.
I don't get why is B equal to 1.
So from node I, there is a probability B to go to I minus 1. And so from node I plus 1, there is a probability B of going to I. And then from I, there is a probability A to go I plus 1. And so the same from from I minus 1 probability A. That's why they are inverted with respect. That I also hesitated because, yeah, it's like left and right, you always get confused.
I mean, you're gonna have A on the left and B on the right for each node.
For each node, yes. Yeah, thank you. Something that I didn't say. These relations are valid throughout the whole network. So for every, you have one flow with probability A and another flow with probability B.
I mean, it could depend on the node as well, right? Could depend on the node as well, eventually.
Yes, yes, and remind me if I don't say a comment, if I make a comment about it, remind me, please. I brought it, but then,
Yeah.
because, yeah, that's another very cool thing of doing, dealing with networks. That it's much easier at the end to study whatever, well, whatever not, but you have much more freedom. Okay, so we can develop this. So this is equal to 1. So we have A U I minus 1 plus B U I plus 1 minus U I. And then we add and we subtract. I have to get the indices right, yes. So U I minus 1 minus we have U I minus 1, and then A half U I plus 1 minus A half U I plus 1. Okay, and then you can consider that this, you can break it in A halves plus A halves, and the same for B, okay? And if you develop everything, I will scan this, there are all the calculations. If you are able in reading my hieroglyphic writing. So at the end, what you get is 1/2 A plus B, and then you have U I plus 1 minus 2 U I plus U I minus 1, which you should recognize. And then the meaning of these parentheses will be clear in a second. B minus A U I plus 1 minus U I minus 1. So if we consider that there is a discretization delta x squared, that it's always 1 on network for convention, it's simpler. So here something similar, again, equal to 1. Okay, you see that there are some coefficients. This is 1, but then of course there are some, you can do it in a more rigorous manner. And for this, I put the paper, Dept et al. 2016 in the Dropbox. And Francesca Dept is a physicist in Perugia, and she works on diffusion on networks, and they made a derivation starting from statistical mechanics. This is in the Dropbox folder. But then you see that this term is the second derivative, so is the Laplacian. But then we have something more, and this, if B minus A, so in absolute value, is the difference of boosts between one direction and the other. So it's like to have a differential flow. don't know, a uniform magnetic field, for example. So it's something that biases the diffusion uniformly in the whole network. Okay, so we can say that the directed Laplacian, a drift, yes, a drift. It's a transport term. It disappears, exactly. So we can say, because it's not exactly the same thing, but we can say that this is equivalent to nabla squared plus a transport term. The cool thing is that of network, so in a lattice, okay, it's equivalent. But then on network, you can have, as you said before, this is the comment, that you have a difference in probability at every node. So we know that the embedding is the drift, but then while it's very easy to represent this on continuous, if you have a, I don't know, a random graph where in each node you have a different drift, you cannot do the embedding, but then you can study it on networks. Okay, so now we can define more rigorously the Laplacian, that from now on I will just call L. Also because in 2 minutes I will have to define another L. So it is defined Lij as Aij minus K out I delta Ij. Because when the network is directed, we have to distinguish between the degree out, which with the convention that we use, it's not the same for everyone, is the sum over J of A J I, and then the in degree. So the flow that is incoming. And now when the network is directed, we can really talk about incoming and outgoing more with more meaning. A I J. When a network is balanced, so as in this case, that it's just a discretization of a lattice, these two coincide. In applications, many times, that's not the case. So that's why we need sometimes another Laplacian. So if the network is symmetric, is balanced, so even if it's directed, you have that K in is equal to K out. We have the homogeneous state, so it's good to do Turing. If we have a K in equal K out. So if K in equal K in out for every I, then it's balanced. So now if we have a homogeneous solution, okay, then we have, we know that when the network is symmetric, this is 0. And now we have Aij minus delta Jk out. So Aj and then we have minus K out. and this is K in, K I in, and this is 0 because the two are the same. So for balanced networks, the Laplacian has the eigenvector, the uniform eigenvector associated to the 0 eigenvalue. You can also estimate the spectrum. This is in general for also where it's unbalanced with the Gershgorin theorem. I don't know if you heard of it. I don't remember if I wrote it because it's a strange spelling. Okay, so I will just say Gershgorin. You can give an estimate of the spectrum based on some properties of the Laplacian. Now, in many applications, the network is not balanced, and so you don't have the homogeneous state. And to be able to still study Turing, you need to define a new Laplacian, Lij, that is Iji minus K out I delta Ij. So we invert.
How are you going to get the homogeneous solutions? Like, how do you get the homogeneous solution in the first place?
So it means that in every node, there is the same concentration of both species. So there is no diffusion between the nodes. There is no gradient, and it's homogeneous. You impose that there is a homogeneous solution. That's your starting point.
That's because the equation for the directed graph,
Mhm.
so you're going to take like this on what instead to make the
Yes.
supposing the homogeneous solution.
Yeah.
That you're going to have that f of g being 0
Yes.
plus the sum being 0 as well.
There's some.
That there's this sum being 0 too.
Yes. I don't understand the question.
I thought it would only make sense if you are not on a directed graph, but only symmetrical graph in the first place.
So now imagine that you have a drift, but then the concentration is the same. So that nothing is happening.
Yes. So
There is no difference between the nodes because it's all homogeneous. Now, if this is unbalanced, that's not true. If you need to define this Laplacian. Okay, but as usual, you solve one problem and you have another one. So now, imagine that on every node in the network, there is a certain quantity of mass. And so this is the total variation of the mass. Should be a vector, okay, whatever, it's a vector. And of every species. So you should have that the mass conserves. Okay, but now, just by studying the diffusion with this Laplacian, so you have J Lij xj, some I some j a j I minus k I j xj. Let me see if I okay. So now sum over I and j, okay, ji. And then here you sum only over I because there is the Kronecker delta. K out xi. And here, sorry, there is an xj And now I sum over I, and this is kj in xj minus k out I xi. Okay, you can just change the indices in the same thing, but then you see that this is not zero because the sum over the degrees is not the same. This, in a certain sense, makes sense physically, because if you have a network that is unbalanced, so globally you don't have the same incoming links and outgoing links, it's like that there are some source terms and some sinks. So it's okay that the mass does not conserve, it makes sense. However, with this operator, we cannot talk about Ficcan diffusion because it's not anymore a Ficcan diffusion. It's actually, the system cannot be considered isolated if the network is unbalanced, but still we cannot talk about Ficcan diffusion. But then on networks, we always see spreading of epidemics, of opinions, so you don't really need the conservation of mass. So when next time I will talk about Turing patterns on non-normal networks, they're not balanced. So you will assume that I will use this Laplacian. Okay, so I will leave this. I don't remember if there is this calculation. I think in the book Newman about networks, there are all these things about diffusion. I didn't put it in the Dropbox. Now, again, reaction diffusion system. Let's go to Turing. Du sum Lij uj. I probably should leave this equation on a corner and never delete it. Okay, and now L is asymmetric. And balanced. So we studied the case where you always return to the starting point. We can repeat exactly the same procedure. Okay, networks that are balanced are they have an orthonormal basis of eigenvectors. They're called circulant. And already this definition gives an idea that you go back from where you started. So just an anticipation, they are the only kind of asymmetric networks which are not non-normal. Then I will tell you at the end or next time. So now we can repeat the exact same procedure and get yeah, we are studying now. So we studied it on symmetric network and now asymmetric network, but still in a controlled case.
So it's directed.
Directed, see, directed, yes. GU and then GD. Lambda alpha. But now the network being directed, so asymmetric, now we have that lambda alpha is in principle has a real part and an imaginary part. Okay, and the real part is negative semi-definite. Actually, we can say directly negative because we know that it has the zero eigenvalue. So when the imaginary part is non-zero, we have that the real part is negative. Okay, and now there is a long and tedious calculation that I will skip because otherwise after lunch it's the perfect time to fall asleep with all these calculations. But then, so you'll find a part on the notes, and then on the paper Aslani et al. Of 2014, it's a Nature communication. They were the first one to study Turing theory on directed networks. And so, well, you can actually find an analytic condition for the instability. It's all algebraic computation. What is interesting so you have your dispersion relation, and due to the asymmetry, due to this part, that when you compute the determinant, okay, it loses the I, so it sums, takes a minus, but then at the end in the calculation it sums. You have a gain, and this is really cool because etc. And then you go back to the continuous curve. So you are stable, but actually no, you are unstable because of this effect. And you can visualize it in the complex plane. And then, sorry, minus the real part and then the imaginary part. That you, in a case like this, you have the stability region here. So where your spectrum is real, you are stable. But then as soon as you introduce an imaginary part, you cross the instability region. And this is true also in other applications for engineering, like synchronization of power grids. If you have asymmetry, it's much easier to go unstable. And this condition can be found analytically, and the details are in the paper. And now again, if we look at the Brussellator model. Yeah.
Instability region arises from the fact that you have a non-zero imaginary part.
A non-zero?
Imaginary part.
So not exactly. Let's go again to the Brussellator. I think it's the best way to visualize it. So this is the instability region that is fixed by the model parameters and the diffusion coefficients. So once you have FU, FV, GU, GB, DU, DV, this is given, you cannot change it. But the instability of the network, so let's say that you are in a certain point in your parameter space. Let's say you are here. Okay, so you are here, it means that your dispersion relation in principle is negative, and this instability region that you can visualize in the complex plane is away from the real part. So if instead you would be here, so here it would mean this. And so if you look at the complex plane, that your instability region would do something like this. It would close. Okay, so you are here unstable, and then here you reopen. There is a mapping between these two. Because, okay, something that I didn't say, that the spectrum is so you can reflect it from one side to the other.
You have the national solution because there is an imaginary part. Otherwise,
No. This part, there is always. That there is always. No. There you always have it. Even if it's symmetric. But if it's symmetric, you just don't cross it. So in the classic case, when you have continuous support or symmetric network, it's your region of instability that crosses your real axis. And that's why with a symmetric network, you hit it. Okay. But then if you go here outside the Turing region, and this is just a triangle because for the Bracelator it's like that. If you have another model, you have something different. But here inside you have Turing patterns, outside you don't. And here we don't go because the homogeneous equilibrium is not stable. The fixed point is not stable. In this setting, you would be below. If you look at the real dispersion relation, if you look at the imaginary dispersion relation, again, you would be outside because in the continuous case, you just are, you are the real axis. And if it's a symmetric network, you are on the real axis. Thanks to the asymmetry induced by the topology. Now, this is fixed. The model and the diffusion coefficients are fixed. But thanks to the topology, thanks to the asymmetric network, you can still reach the instability. And that's why they called it topology-driven instability. It's still diffusion-driven because you wouldn't have this region without the diffusion, the difference in the diffusion. But then it's the topology who allows you to extend your region of instability. And this, how big this is, depends on the networks. Depends on the spectrum of your Laplacian. There are networks with even asymmetric with real spectra, so you don't have a particular gain. You have other things. We will see this next time. So also in your application, you need to choose the network you are using. It depends on your objective. Do you want to be more stable? Do you want to be more unstable? And just like curiosity, that this equivalence between this and the drift, it's something that we understood a lot later. And actually, there are some works in the 90s done by Rowiski and Metzinger, two physical chemists, and I put them on Dropbox, who study Turing instability with drift, with a differential flow. And at the end, if we compare the results, they are very similar. Of course, here we have finite size effects. So it's really a drift. Okay. So last thing, and then I arrived where I wanted to. Questions on this? So if the network is balanced, we know that there is an orthonormal basis. If the network is unbalanced, but still diagonalizable, we can still compute the dispersion relation because we can multiply by the left eigenvectors and still do everything rigorously. What happens if the network is defective? It's not diagonalizable. So we have our linear perturbation, so linearized perturbation of the homogeneous equilibrium. And we had a 2n times 2n system. Plus d Laplacian. So this is the Jacobian, the 2 times 2 Jacobian, the identity n times n, the diagonal matrix of the diffusion coefficients, and the Laplacian. And then of course, otherwise it doesn't make sense. And this encodes all the perturbation of every node for every species. Okay. By expanding this on the basis of the Laplacian, we could get to n 2 times 2 systems. Now we cannot do it because there is no basis. So we use the Jordan form, the Jordan canonical form. And we can determine a matrix P of the same dimension so n times n, invertible, such that we have P minus 1 L P equal to a matrix B, that is the matrix with the Jordan blocks. B1, BL, and every block, for example, J, is a matrix MJ times MJ, where we have the sum over J of MJ is equal the dimension of the Laplacian, and VJ is the matrix with J eigenvalue on the diagonal and then 1 on the subdiagonal. So this is the Jordan form. If the network is connected, we know that lambda 1 and only lambda 1 is 0. And so B1 is a scalar, is 0. Okay, the first block is 0. Okay. Now, I will delete. Can I delete? I don't know if you say delete in English. Erase, yeah, thank you. I'm too used to the computer. Okay, so I've been saying for 3 hours, delete, delete, delete. Okay, and that will be forever on YouTube.
That will not be deleted.
Huh?
They will not be
They will
deleted.
not be deleted. Now we can say delete. Okay. So after I've erased, we can still change the basis. And so we define a new the perturbation in a new basis. So x equal q minus 1 Greek z, where q minus 1 is equal to the identity 2 times 2 Kronecker product of P. And now I erased what I needed, so I will rewrite it. J0 in plus d L. Now we rewrite the perturbation in the new basis. So x time derivative q minus 1 z, and so we have e I 2 times 2 p minus 1. Yeah, sorry. If we put here minus, yes. So if we put here minus 1, it's also there minus 1, because being the identity commutes. So yes, formally I should have said this, and then q minus 1 would be p minus 1 tensor Kronecker product I minus 1, but the identity is invertible, and then we can, it's not commutative in general, but with the identity, yes. Yeah, sorry about that. J0 in plus, I wrote too big. And then we have y2 e minus 1, and then sorry p, and then q minus 1 z, because I multiplied for q minus 1. Okay, and here I'm just adding the identity. So no, actually I'm multiplying left by q minus 1, and here I'm multiplying by the identity, and so then I recover the x. Now all these I will show you in a second, does not have any effect on J0 times the identity, but it does on the Laplacian. So all these in the new basis is equal to, sorry, to J0 in plus d Kronecker product of the matrix B that I wrote before, X. Yes. Do you trust me, or you want to see a trace of the calculations? Shall I show it?
The D is there.
The D is the diagonal matrix of the coefficients. So the two, these two, they don't have any these two, they don't have any effects on this because it's the identity. So it's a tri-diagonal matrix that doesn't have this is a matrix who only has effect on L and transforms it. I erased it in B. Okay. So now we are almost there. We have this equation. So we didn't exactly decompose all the perturbation, one perturbation for every mode, but then we have something that looks quite good, especially thinking that we are dealing with a non-diagonalizable network. And so now we can rewrite the x as a vector, x1, it's a column vector, x2, xl, where each x has dimension ml, which are the dimension of the Jordan blocks associated to that eigenvalue, m2, and then we know that this is just one. So, sorry. Sorry. 2 times ml, because so ml m2, because every x, so x, for example, x j generic, that's u delta u j 1 delta u j2, and then also there's delta v. So every perturbation it's two species, delta v j1, delta v jl. For every block you have the two perturbation. Okay, so now we have that x1 is simply j0 x1, because lambda 0 is 0, and so b0 is 0. But then all the others, generic j, we have j0 the matrix with all the j0s plus the block bj, so lambda j but that was multiplied by the diffusion coefficients. Okay, and so we have sorry, otherwise the dimensions don't match. Lambda j is a scalar multiplied by the matrix of the coefficients, which are all 2 times 2. So this is 2 mj times 2 mj, where mj is the dimension of the Jordan block associated to the eigenvalue lambda j. So it's equal to the degeneration of that given eigenvalue. Okay, so this matrix at the end, and then of course xj. So this matrix, this would be xj okay, where we have all the perturbation, is equal to a matrix that is the Jacobian, so fu, fv, gu, gv at blocks, and the rest is all 0. So only in the diagonal you have the blocks. And this other matrix that now I don't have enough space, so I will go here. This other matrix is just du lambda j 0 0 du lambda j. But then it also has the block below, du 0 0 dv. So, well, you can redo all the calculations at home with more space and more paper. But then the idea I want to give you, so if you look only at the first block, you see that it's exactly the matrix that we had before. Okay, so it's the coefficient plus of the model plus this, and then it's exactly 2 times 2. But then there is this subdiagonal. It's not exactly a subdiagonal, it's like a block subdiagonal that is due to the degeneration of the eigenvalue that doesn't have as many eigenvectors as their multiplicity. Huh? This?
Yeah.
It's here. This?
Yeah.
Is this? Yeah, I would for this actually I would need three blackboard. But then so this is the block here, and then yeah, it didn't fit, but this is the block here, and then here this block is repeated as many times as the degeneration. Okay, so finally, thanks to this, and then I'm finished. We can have something like a dispersion relation that we can even compute. Okay, so we have that for the first for every mode, so if you consider the generic J mode, and then we have that the first perturbation delta U1 J delta V1 J is equal to J0 delta U1 J delta V1 J plus lambda J, then we have the diffusion delta U1 J delta V1 J. So this is exactly the 2 times 2 system. But because of for every J, this is like the alpha as before. So we have that the 0 mode, this is the dispersion relation, for example. Let's make it stable, so it's more interesting what's happening. Okay, this is the 0 mode that we always have. We don't have the diffusion part, and it doesn't have the generation. And then this mode, let's say it's here. This we can compute in the dispersion relation. But then, because of the degeneration, we have that for k that goes from 2 to the dimension of the degeneration, we have that delta UK J delta VK J is equal to something like this, delta UK J delta k j k j j. So it would be the same, but no, because we have something more. We have that block, that sub block of the diffusion coefficient gives another contribution. So we have now d delta uk minus 1 j delta uk minus 1. Okay. And this is for every mode that is degenerate, for the dimension of the degeneration. So this we can compute. This we cannot. And we have this contribution that is a positive contribution. Okay, so here you might think that you are stable, but actually you have a hidden contribution that makes you go unstable, but you cannot quantify it. The only thing you know trivially is that if this mode is unstable, sorry, all the others will be unstable as well. But here you don't know. And so next time I will talk about non-normality, because networks who are non-diagonal, non-diagonalizable, they are non-normal, and it will be clear why.
It's not only because you know the image one.
We cannot know, because we don't have a basis. You don't know in which direction this is going.
Like the variation.
Yeah. So there might be a way to solve it. This is something actually new. We have a master student working on this, seeing how these generalized eigenvectors can contribute to the path, to the shape of the pattern.
You know what the matrix is, right? For that.
Yeah.
Yes, think of that. I don't know. You just treated those WI's variables. That's one. It's something. You saw a even from time. Why isn't that the case? You start with one, and then the second one will involve solutions that you found from both fine. So on and so forth. So you get one. Why does it then make sense?
So yeah, but I'm not sure that you can solve it. Because I don't know, you have contributions of other directions. And especially this would depend on the initial perturbation that is random. So there are some methods to know where the perturbed spectrum is going with the, for example, continuation methods. There is also the pseudo spectrum that is something related to non-normality. But then you cannot have an exact form. It depends every time on the perturbation. Because it depends, I don't know. For example, let's say that this has the generation 2, BMJ, and it's exactly the one here. Okay. If you hit a direction that is unfortunate, like if this is a direction that doesn't give a contribution, then you stay stable. So it depends on every perturbation. You cannot do it analytically. So this is analytical. And you are sure that any perturbation that you have, so for example, if you are stable, you know that any perturbation of any kind, or even infinitesimal, because the fixed point loses stability, you know that you will go away from the homogeneous state. But here it's perturbation dependent. So of course, you know that there is a contribution, but a priori, if you don't do the simulation, you don't know what's happening. So you know, with a like I, in Italian we say occhiometro, so that you measure a bit by sight. That this case is dangerous. And if you are like this, you are safer. But then this, it's your random perturbation. So you at the beginning becomes fixed point plus something that is random. And so you are not really sure how it evolves. But yeah, it's something we've been thinking about. And actually, I'm telling you the story on the opposite side. So now you see that if you are stable, in principle, you could be unstable, and then next time you will see all the things of non-normality. But we thought it on the other way, and we got to this after. If there is a way to solve it analytically, we are very happy to take suggestions. And we have now a master student who's doing simulation and trying to see how the generalized eigenvectors can affect. Okay, I finished where I wanted to finish, so I'm happy, and thank you for your attention.
So very good. So see you on Thursday. Bye, everyone. Bye-bye.